exam, the the problems are going to assume you remember all your basic formulas like area, perimeter, volume. And if you don't, you need to have them like printed out somewhere. Okay, just like basic shapes like sphere, cylinder, cube, all that crap. Just have it somewhere. And if you know them all, that's great. All right, so this is some notes right here. So let's start with the first example. So find the length and width of a rectangle that has the given perimeter. And the maximum area. Okay, the perimeter that they're giving you is equal to 72 meters. Hold on one second. Turn on the air in here. It's freaking hot. So picture this, right? You're trying to build a fence. Maybe you're trying to fence in some animals. Maybe you're trying to fence in some vegetables. I don't know. Who knows, right? But you want to maximize the space inside. So the fence or whatever we're talking about has to be 72 meters. Increase the width. The increase is what will give me the maximum area. So depending on the perimeter, that will basically put on limits and requirements on this. Okay, so that's what we're doing. But let's get started. So P is equal to 2L plus 2W. So this is the formula you need to know. It's not given to you. 2 times the length plus 2 times the width is your perimeter, right? Also, assuming everybody knows the area formula is length times width, right? And if not, well, there they are. Step one. Okay, so I'm going to plug in perimeter and solve for one of the variables. That's what I'm going to do. So plug in 72 meters and plug in, yeah, let's solve for it first. Plug in the perimeter. I'm going to solve for L. Okay, so I'm going to subtract 2W, divide by 2. Let me know if you need more details. This is L, right?
Right.
Okay. If you need more algebra details, let me know. So we're going to plug this in into the area formula. That way we can get into one dimension instead of two. Because we have our derivatives we've been doing is only respect to one variable. This will be easier. So step two, plug in L, and we'll have nothing but W's. This will become 72 meters minus 2W over 2 times W. I'm not going to put the meters because it's a little distracting. It doesn't matter. You can if you want. Doesn't matter. Just remember everything's in meters. So distribute your W. divide by 2. That would give us 36W minus W squared if you do both at once. Is that okay so far?
Yes.
Can you explain the W square?
Why is W squared?
Yes.
Okay, let's show some steps. So first step, divide everything by 2. You agree that this is 36 minus W. Right? Then distribute the
Yes, sir.
W in, and then we get this. Is that okay?
Got it. Thank you.
Yes.
Okay. So now we have a simple equation. That's our area formula. So A is equal to this. Take the derivative of both sides with respect to, let's say, with respect to W. Trying to maximize the area, so we're going to do W. So, no, I'm running out of space. So that implies that dA dW is equal to 36 minus 2W. So this is technically our third step here, but that's okay. Make some room here. Find A prime and set to 0. Now wait a moment and I'll turn the page.
Wait, not yet. Not yet. Need to finish writing this. Hold on. W. Step 3 is to find a prime set equals 0. Okay. Okay, go ahead.
So any question on the derivative or the substitution? It's okay.
Yeah.
Okay,
Yes.
so let me know anybody at any time. I can always turn it back. Okay. There's no problem. So we're going to get 36 minus 2W equal to 0. To solve, that would be what? Negative 2W equal to negative 36. So W equals 18, right? There. So right here we are finding critical number. All right. So that's my critical number. Step 4. Use first or second derivative test. W equal to 18. So I'm gonna do first, I guess. Doesn't matter. Here's the critical number. And there's 19, I guess. So plug into the derivative, plug in 0. That's gonna be 36 minus 2 times 0, which is positive. Right?
Right.
Then dA dW at 19. Well, that'll be a negative, wouldn't it?
Yes, it would.
2. So we got increasing, decreasing. So the maximum, again, what are we maximizing?
The
perimeter of a rectangle.
area.
Well, we have a fired perimeter, and we're using that to maximize the area.
Yeah, we're using it
So,
to maximize the area.
Like if you had a certain number of materials and you want to maximize the enclosed space, that's the idea, right? So maximum is happening at when the width is 18. So this is enough to find the length as well, right? Because we said length is equal to 36 minus W, which is 36 minus 18, which is 18. It happens, so it just so happens that both a perfect squared would be for this example, not always, right? Just this example. But that particular perimeter, this is the best width and length.
Okay.
Anyway, does that make sense what we're doing?
Yeah, makes sense.
Like when we were doing those other word problems, right? We had change in volume, change in radius or whatever, but this time we want to make sure we have the maximum. Okay. It could be minimum too. Depends. Depends what we're talking about. This next one will be a minimum type, but the approach is the same. So I want you to think of the big picture. Doesn't matter what the hell we're talking about. If it says maximize this given something else, I need to take you want to maximize and set it to 0. Nutshell, that's what we're doing, right? So let's not make this harder than it is. They told me to maximize this. They set it right here. So I have to take a derivative of this, but I wanted it in one variable. So I used the perimeter because they gave it to me and the perimeter formula to make this equation simple. And then we've been talking about maximizing and minimizing for a while. So we did that. That's it. That's all it was. Any questions on this first example?
No, in fact, I wish I had this explanation when I was doing the homework.
Now it makes more sense, right?
Yeah. So your connection is kind of jittery.
Oh,
It's
is
not
it?
the best.
Yeah, my internet's not the greatest. And I'm trying to, I'm updating this PC behind me, so I think that's eating a lot of bandwidth. Sorry about that. Yeah, maybe that'll help. Okay, next one. This thing's number 4 in the homework. Find the point on the graph of the function that is closest to the given point. So I'm going to graph it for you so you can see what exactly they want. We'll come right back to this. Can you all see the grapher?
Yeah, we see the graph. We see the graphing calculator.
Okay. Find the question. So here's the graph they want us to a function. And they gave us a point. I haven't written it down yet. -5, comma 3. All right. So they want to know what's the point that's closest to that other point. But one of them's on the graph and the other one's over there, right? So what point on this function is closest to that point? Okay, so that's the goal. That's the question. Let me write down the function and the point real quick. So f of x or y is equal to x minus 1 squared. The point given is -5, comma 3. So what you want to do is use the distance formula, but optimize the distance formula. Okay. So this is the formula from back in the day. This should be familiar. So optimize the distance formula. So since we already have y, we can plug it in. And we got x1 and y1. So we're going to use this version of it. The general x minus x1 plus general y minus y1. So we have x1 and y1, and this is our y right here. Okay, that's why I read this way to remind you. So x minus x1 squared plus x minus 1 squared minus 3. So I'm plugging this in for this y here. Okay. Things in terms of x on purpose. Make it look pretty. And then we'll be good. So FOIL this out, that's going to be, well, let me do some, this would be x plus 5 squared, plus this will be x squared minus 2x plus 1 minus 3 squared. Okay. Let's multiply all that garbage. That'll be x squared plus 10x plus 25. That will be x to the 4th minus 2x squared 4x plus 4. There we go. Hold on, let me double check that. Yeah, it's not that simple. Sorry, that's a mistake. This is a trinomial. Technically, it's this, right? So x squared times that nonsense is going to be x to the 4th. Let's see if I can fit it in here. Minus 2x cubed minus 2x squared minus 2x cubed plus 4x squared minus 4x plus 4x minus 2x squared plus 4x plus 4. And that should be negative 2x cubed minus 2 plus 2. So that'll be 0. No. So minus 4x cubed. Okay. 4x squared minus 2x squared minus, so the x squares are gone. Negative 4x plus 4x is an 8x plus 4. Okay, here it is. Sorry about that. So when you square this nonsense, you'll get these 4 terms. Want to double check. Anyway, so far, you guys good?
We're hanging on.
Yes, sir.
Make sure they are turned on. Again. All right. Combine all like terms. That'll be x4 first. Minus 4x cubed second. I guess there's an x squared right there. 8x plus 10x is 18x. 25 plus 4. All right, who cares? So there it is. So now we can optimize this. So the good thing is all we got to do is maximize the inside. We don't have to deal with the square root. Okay, it doesn't really matter. If we maximize the inner part, it'll just be in there, so it's all fine. So
When I was first doing this problem, the
optimal
homework,
sorry, go ahead.
when I was first doing this problem in the homework, the way that the Cengage explained to optimize this is to find the derivative of this equation here, like the first derivative.
Yes, we need to find the first derivative, but we don't need to use the entire square root part. That's what I'm saying. So we're gonna optimize this instead, the inner part. Otherwise, we're gonna have a chain rule, and then it'll be complex, and we don't need to do this. The only issue is that this is a higher powered function, so we're probably gonna have to do synthetic division. Do y'all remember your college algebra stuff?
I don't think I've taken college algebra since 2019 or 2020. That was 5 or 6 years ago.
Gotcha.
It's been a long time.
Okay. So I'll do on the next page. You guys good on this page?
Yes.
Yes.
Yeah. The next step we'll find G prime, one I just labeled, and set there we go. So G prime will be 4x cubed minus 12x squared plus 2x plus 18. So set this to 0. I'll do the next step. So this is where I need synthetic division, so we can't solve this the easy way, I don't think. Let me see. No. Let me see. Yeah, we'll have to do synthetic. This is how you do it. So you take the constant and find every possible factor and divide that by every possible factor of the leading coefficient. And those are all the possible zeros. So the possible zeros are plus or minus 1, plus or minus 2, 3. So I'm doing the 18, factors of 18. 6, 9, 18. Yeah. That's all of them. Factors of 4 or multiples will be 1, 2, plus or minus 1, 2, 4. So divide these interchangeably, and those would be all the possible zeros. So basically, the possible zeros are plus or minus 1 divided by 1, 1 divided by 2. Oh, let's do it this way. 1 over 1, 2 over 1, 3 over 1, 6 over 1, etc. Get all the whole numbers first. Then do the fractions of 2 over 1, I already have that. I'm sorry. 1 over 2 is the next one. 2 over 2, which is 1, so I already have that. 3 over 2, I don't have that. 6 over 2 is 3, so I already have it. 6 over 4 is a what? 3/2, so we're good with that. 9 over 4, don't have that. 18 over 1, already have it. 18 over 2 is a 9. 18 over 4, what is that going to be? 9/2, right?
Yeah.
Okay, so that's every possible zero event. It could be. I don't know which one it is, but it could be. I always start with 1 and -1 because it's easy. So this is synthetic division. So the first step when you do synthetic is to find all the possible zeros and then write down all the coefficients in descending order, making sure you have every degree. If there's one missing, you have to put a placeholder. Got to put a 0. So we got 3, 2, 1, 0. So you got 4, -12, 2, 18. Bring down the 4. 1 times 4. -12 plus 4. 1 times -8. Add that up. 6. 1 times -6. Add these up. 12. So let me go through it again. So you put the 1 there, then you put all the coefficients of your polynomial. But you got to have every single power included. The first one, you just bring the 4 down. You bring the leading coefficient down to the bottom. Then you do 1 times 4. You get a 4. Then you add these up. -12 plus 4 is a -8. Then you do 1 times -8. There's my -8. 2 plus a -8 is a -6. So now 1 times -6, there it is. 12 plus a -6 is 12. I did not get a 0, so it is not a divisor. So now I do it again. I'm going to do it again over here with -1. So 4, -12, 2, 18. Bring down the 4, -1 times 4, right there. Add these up, -16. -1 times -16 is a positive. 2 plus 16 is 18. -1 times 18 is a -18, which gives me my 0. That's what I wanted. So that means that this is a 0. So -1 is a 0 if I plug it into G prime. That's what this means. It also means that it's a factor. If you remember the fundamental theorem of algebra, right? It says if it's 0, then it's also a factor. It can be written this way. So here's the note. So using synthetic division, so G minus the factor times this leftover is the new polynomial. So basically we pulled out a factor from the entire thing. Okay. So that'll be 4x. So we started with a cube, so now we have a square. Right? So this is x plus 1 times 4x squared minus 16x plus 18. All right. Any questions on the synthetic part?
If we're pressed for time, is there like a quicker, more efficient way, or is this all we're getting?
No, this is the best way.
Okay.
Sadly, yeah. Once we get to quadratic, though, you can go back to quadratic formula or whatever you want, right? But because
right.
we were not in, we were higher than quadratic, we have to do synthetic.
Okay.
So usually computer programs are doing something like this in the background. Okay. But by hand, this is what you're supposed to do. Okay. So I already forgot. What the heck were you optimizing? It's a while ago, right?
We were trying to optimize for
A given point.
Yeah, so we got lost in the weeds of the algebra, trying to factor to find the critical number. That's what we're doing right now, right? We need that to for the point, the closest point. Okay. So we're gonna have to do a first or second derivative test. So we'll do a first one on the next page. But do you all see the algorithm, the pattern here?
yes.
So you basically keep choosing 1 or -1, 2 or -2, 3 or negative until you find one. Once you have one, then you're good. You can once you get to power 2, we don't have to do this anymore. But you could, but you don't have to. Because we have many techniques for quadratics. But anyway, we'll use this as our critical number. We're going to test x minus 1. Oops. Okay, so here's the critical. So plug in, let's say -2 into the derivative. Let's see what we get. 4 times -2 cubed minus 12 times -2 squared plus 2 times -2 plus 18. So that's the original. Add all this garbage up. It's going to be negative. Yeah. So this will be -32. This would be more negative. Yeah, this is minus. I don't care the number. I don't care what the result is. Negative. G prime of 0. That's an easy one. Be 4 times 0 cubed minus 12 times 0 squared. Oops. Plus minus 4 plus 18. That's positive. So we got decreasing, increasing. So minimum, and that's what we want. That's what we want, right? Minimizing the distance at x equal to -1. So plug this in. F of x to find the y value. Back to the original. And by original, I mean that, well, I should say, no, it would be f. Because we want the point on the graph, right? That's what we're searching for. So put it in f. So that's right. So f of -1 is equal to -1 minus 1 squared, right? Because it was x minus 1 squared is what it was. It's a parabola. That gives us a 4. So the closest point on f of x equal to x minus 1 squared to the point was -1, 4, right? -1, 4. No. Sorry. This point is closest to the point in question. Closest point on f to -5, 3, here it is -1 comma 4. So optimizing the distance formula told me the closest point on below to this. Okay, that's what we did. So here's our conclusion and what we were trying to do. You guys cool on this one? And any issues at all?
No issues, but honestly, if I were pressed for time, I'd probably just start plugging random numbers in I'd probably just start plugging in whatever possible zeros we have into the formula we got and just see what comes up as 0 and make that my x variable. If I'm pressed for time, which I probably am going to be on this exam.
Oh, I don't think on the exam I'm going to give you something that would require synthetic division, although synthetic would be faster because you need because there could be multiple zeros.
Okay.
Because if you find one, that's great, but you don't won't have the factored form. So you would have to go through every single zero to make sure you're good. Because if you had the factored form, then you could do quadratic, and then you'd have the rest. But if it's a
Okay.
fourth power, you'd have to find 2 zeros with synthetic, and then you could do quadratic. But
Okay.
again, this is a homework question. They're supposed to be a little harder than the exam. The exam's not supposed to be that much.
But if it's up to a third power, you only need just 1 0.
Yeah, so once you find one, but I didn't find them because I was already taking too damn long on this question. But I should have tried to solve this guy.
Okay.
safe. But I already knew there's only one that mattered. So, but technically, if you didn't know, you should. Graph that real quick. Yeah, this has no solution.
Yeah.
This has no zeros. So I knew there was only one.
Okay.
That's why I didn't go forward with this. So if you would have tried, you would have got imaginary numbers. And then I would have told you that this is the only critical number, the -1. But
Okay.
if you didn't have this factored, you wouldn't know that, and you'd have to plug in all of them to be safe and to be sure there's no more, which would be kind of annoying. I think this would be faster
Okay.
because once you find one, you're pretty good. Let's see if we have time for at least one more optimization problem because they take forever. We've only done like two. As you can see, it takes a while, right? But you guys are good. I'm going to move on to the next one. So this one's a pretty cool question. So this is the optimizing a box, the volume of a box. So we have a piece of cardboard. That is 14 inches by 10 inches. And we will cut out the corners. And fold it up into a box. Determine the height of the box that will maximize the volume. So when you read these questions, first thing you should ask yourself is, okay, what am I optimizing?
Are you optimizing the
Right, what do they want us to do?
they
Because
want us to
optimizing
find,
means
they want us
max or minimizing.
Area?
Maximizing.
yeah, they're asking us to maximize volume.
Okay, so that means we gotta take derivatives of a volume formula. What volume formula do we need? Because they didn't tell us anything.
A
Length times width
cube?
times height.
Yeah, I guess it would be cube, right? Because it'd be a box. So I guess technically a rectangular prism, which is a cube is technically a subset of that, right? So length times width times height, correct? Define volume.
Yes.
Okay. It helps to graph or draw the figure. So I got a card piece of cardboard. It could be a square, could be a rectangle, could be a cube, could be a rectangular prism. I don't know. But it's a general four-sided shape. General rectangle that I'm gonna fold. Now I said it's 14 inches by 10 inches, so 14 inches, 10 inches. I'm gonna cut these corners out, right? So I'm gonna call these corners. Do you agree that if I fold the corner up, that would be the height?
Yes.
So then this length right here, or this dimension is technically the height, right? This is gonna fold up. So if that's true. Once I fold it, what's the new uh what is this side gonna be after I fold it up? Like from here to here.
Um,
What am I removing?
you're removing the corners.
And how big are those corners?
I would say that they're
Right, we're just look at this one side right here. It's 14 inches before I cut them out. What
okay.
am I? I'm cutting out an H and an H, right?
Mm-hmm.
So do you agree that the new side would be 14 minus 2H?
Yes.
Cutting out two corners, right? So what do you expect this side to be?
10 minus 2h.
10 minus 2H. Okay. So that's the volume I'm going to use. Then what is length equal to? The length of the box,
Yeah,
not
I would
the
I would say at length
rectangle,
is
not the piece of cardboard.
I would say at the length it would be width times height divided by volume.
I mean, yes, technically, but I mean like relative to this cardboard, it would just be this here, right here, right?
Mm-hmm. Oh, okay. Okay.
And then the width would be here.
Yes.
So now we can get everything in terms of height, and we don't have to worry about multiple dimensions. So volume is this substitute, that would give us 14 minus 2h times 10 minus 2h times h, right?
Right.
Boil all the, or multiply all this out. And then we have one dimension and something to maximize, okay? So multiply this, we'll get 140 minus 28h. 2h times that is negative 20h plus 4h squared times the h. Add all that up. Going to be 4h squared minus 48h plus 140 times the h. So finally we got 4h cubed minus 48h squared plus 140h.
Wait, hold on. I feel like I might have missed something. I feel like I might have added an extra h variable. Let me just fix that. Okay. I see what I did wrong. Okay, I think we're ready to find the derivative or whatever.
Yeah. Now we have the equation, now we have something to find a maximum of, right? You have the volume equation. Optimize it. Find v prime and set it to 0. All right. There we go. Obviously, with respect to height, because everything's in terms of height now, making this much easier. So we got 4h cubed minus 48h squared plus 140h. So this becomes dv dh. Change in volume with respect to height, which will be 12h squared minus 96h plus 140. So 12h squared minus 96h plus 140 equal to 0. It doesn't factor nicely, so we're going to have to do quadratic formula. I'm going to skip that step because I'm pretty sure you know how to do quadratic formula. We're going to
Yes,
use this here.
At least I do.
Write out just in case you forgot, but I'm going to skip to the answer part. Basically, you plug in the ABC. right? So that gives us two heights once you plug it in. 6.08 and h is equal to 1.92. So I'm not going to do that part. But just plug it in, you'll get these two. All right. So the question becomes, which height will maximize the volume of the box? So this time we have two critical numbers. We don't know which one works. So we'll use this time the second derivative test. On both critical values of h. So both h values. So the second derivative is equal to 24h minus 96. So plug in 6.08. Find out if it's positive. Do it again. On the other one. So for the first one, that'll be 49.
192. I already got it.
Yeah, and the second one's negative version. So this is the second derivative test. So what does this mean if it's positive?
That whatever's our whatever we use to get the positive value is going to be our it's going to be our x.
So we're trying to find which one's the maximum by using the second derivative test. So if it's positive, what does that tell us?
That's our maximum. Okay, that's our minimum. Oh, that's our minimum.
Minimum. So this is the maximum. The 1.92 is the optimal size to cut the squares. That gives you the most volume of your box. Given the dimensions of the piece of cardboard.
Okay.
Finally, plug in h equal to 1.92 inches into the original volume V. That'll give us 4 times 1.92 cubed minus 48 times 1.92 squared plus 140 times 1.92. So that's about 120.164 inches cubed. So this is the maximum volume provided that I cut it this way. So that's what we're trying to do. Is there any question what we did?
Oh, that was a really nice example.
Okay. Yeah, let me know, because it's a long one. I mean, they all take forever, so sorry about that. But the higher you go in math and science, it's questions take longer and longer. Like statics are differential equations, you could spend like 2 pages doing one problem. Okay. All right, guys, and we'll stop here. Unless you guys have some